Hi everyone, my name is Ari and welcome to today's exercise on 3D modeling using Rhino and Grasshopper. In this exercise, we'll be working on the Jinji Lake Pavilion project by BIG Architects, a nice example of contemporary design featuring a fluid, dynamic roof structure. Now during this exercise, you'll learn how to model complex geometries in Rhino by breaking down the pavilion's free-form roof into manageable, repeatable components. We'll start by examining the roof's underlying catenary curves and understanding how they create a graceful organic form. Then we'll move over to Grasshopper. You'll explore how to generate these curves parametrically. You'll discover techniques to refine these curves, merge them into a continuous outline, and generate a continuous smooth roof surface out of them. And then finally, you'll learn panelization, dividing the roof into manageable segments, rationalizing the geometry, and preparing the design for manufacturing by flattening double curved surfaces. Now, mastering these skills is crucial because computational design is increasingly in demand across the architecture, engineering, and construction industries. Proficiency in Rhino and Grasshopper opens doors to innovative design opportunities, improved workflow efficiency, and a competitive edge in the job market. Employers value the ability to combine creativity with technical precision, which can lead to higher salaries and greater career advancement. By the end of this exercise, you will not only gain practical experience in modeling and parametric design, but also acquire a skill set that is essential for staying competitive in today's fast-paced design environment. So, let's dive in and explore the geometry behind this remarkable project and learn a little bit of computational design along the way. Let's dive in. Today we're going to explore this fascinating architectural project, the Jinji Lake Pavilion in Suzhou, China, designed by BIG Architects. And it was completed early in 2025. Now, it's a very interesting example of contemporary architecture by BIG. It has this visually stunning, clean, simple shapes that always captures the essence of the projects that BIG is very good at. Now, the first thing you notice is the roof structure. It's fluid, graceful, and beautifully organic, and it almost seems to float, gently draping over the pavilion like fabric, clearly inspired by natural forms. Now, the roof connects 4 independent buildings and is the main architectural element we will focus on in this exercise. If you look closely, you'll find that the roof comprises of repeating elements, each slightly varying to follow a smooth, curving geometry. Now, why is this important for us? I think this roof makes an ideal case study to practice and strengthen our Rhino and Grasshopper modeling skills. We'll begin by modeling the roof in Rhino, allowing us to understand its fundamental shape and geometric logic, and then we'll shift to Grasshopper, and using parametric modeling logic, we'll define and create efficiently and control those independent elements that the roof is comprised of. As you can see in some of these elements, here we have one of those 4 individual roofs basically. And we're just going to model one because the other 4 is basically the same logic. But as you can see here, like these curves that I just drew, they appear to be catenary curves. And a catenary curve is naturally formed when a rope or chain hangs freely under gravity. And that way the gravity provokes that the curve is naturally and smooth. So that's basically what's happening here. It's a simple setup using those 4 boundary curves to create like this smooth catenary basically surface. And then if we go again like here, like this is the panels. So when we have the surface, well, this is a straight line, but if we have the surface set up, we'll take a look into how to create the individual elements basically. And we're going to do that more in Grasshopper than in Rhino. Once we have like I said, the base geometry in Rhino, we'll move to Grasshopper to, take a look into those roof tiling a bit more accurate and also directly see if we can standardize those shapes a bit better. So let's jump right in. So I've set up a quick Grasshopper definition for you guys to follow along. It already has a curve component with some polylines internalized, as you can see here in my Rhino viewport, and these outlines loosely represent the project not exactly, because that's not really the point. The point is more about how we can use a set of input geometry to kind of generate in Grasshopper our roof surface outline. So these are just very simple, 4 simple polyline curves. And those curves we're going to use to generate our roof outline. And for now, I'm just going to use one. And then if done it for one, we just connect, instead of that one curve, we can connect all 4 of them, and it should just work. Just like this. So this is the one we're going to be working with. And what do we need to kind of generate, first of all, those catenary outlines, right? So there's a nice component in Grasshopper that already does that for us. It's under curve and then spline, and it's called catenary. That component's going to do all the work for us. So we just need to provide the inputs for it. So first is the point A and point B, which are the endpoints of that catenary. So we're going to get those by exploding our polyline. So we get the segments that we want. And then with endpoints, we get those endpoints. And we can already directly connect them like this. The other thing we need is the length, how much length we want to give it. So let me get a curve length component. That basically goes in here. If I directly connect it, it's not going to be a catenary, it's going to be a straight line. Why? Because we're not giving it extra length for the catenary component to kind of create that bulge, basically. So we need to add a small factor to this length. So we can do that by addition. And let's add a slider, a simple number slider, just like this. Oh yeah, and the gravity is already set to the -c direction, so that's default, that's fine. And as you can see right now, our catenary arches got created, right? So that's really nice. The only thing I want is to have a little bit more control over how much that factor is per curve, because right now I'm just adding 0.25 to all of them. But as you can see here, most of them work very well. I like how it turns out with just adding 0.25, except this one. I wanted to build just a little bit more. So how can we make that factor a bit more precise? It's using the start and end point, the difference between them basically, and the curve length to kind of create our own factors a bit more precise. So let's do that. So we're going to first get the difference from the z-coordinate from the start and the end, so I know the height difference. So let me go to vector and deconstruct point. And I want to have the absolute value. So these are the, the differences in height. So 5775. So that's the first one. And I want to remap those values. Remap numbers. And let's get the bounds of that list of numbers. Just like this, value. And then my target domain, that's where I'm going to specify my factor. So just going to use from 0 to 2. Just like this. And the curve length. So it's just a number. I'm going to do the same for the curve length. So let me copy this guy over. Just delete this one because this one goes in values. This one goes in here. Just like this. Then a generic value like this. So we have our remapped height, our remapped length, a general factor, so multiplication. We're going to multiply all these values together. Just like this. And those are going to be the input for my plus, just like that. So let's focus on getting these bulges a bit more like equal. So basically I want this one to bulge just as much as this guy. That means that I need to penalize the length a little bit. So the longer the line, the less I want it to basically bulge. So let me move this one a little bit lower. As you can see, it just affected the longest line, so that's really nice. Set it to 0.5. It's like this. Maybe 0.6. And the opposite for height. So if it's a high and lower to like this. So if the height is lower, penalize it, and if not, make it a little bit longer. So as you can see here, this one got a bigger bulge, so that's nice. Now, more or less, they have the same bulge as all of them. And with this one, you can control all three of them equally to kind of get it exactly right, the way you want it. Let me see if I can get it right. Something like this. So they more or less all have the same bulge. 0.4. Yeah. I mean, it's not exact. It's just to have a little bit more control. And that's the process of creating our catenary outlines. Then the only thing we need to do is to kind of create a closed curve. So we need to connect these 2 points as well. And to graph this input, and then create a line between them, just like this. So we have that line segment, our 4 catenary curves. And then with a merge component, we can join them together in one list. And then with the join curves command, we can join them together. Let me turn these off. And this is our outline, our curve that we're going to be using to generate our roof surface. And there's a lot of different ways we could do this. I've tried most of them, but the most cleanest one, and also the one that gives us the most control over controlling the shape of that surface, is called the patch command, or the patch component, which is located here. This component just requires a closed curve as an input. And as you can see, it directly already generated that outline. And there's some extra inputs where we can control that shape a little bit better. Spans, the higher the number of spans, the more control points, and the more accurate the surface is going to follow the outline. So let me increase this a little bit. Let's set it to 30. And flexibility. So the higher the flexibility, like over low number is less flexibility, higher is more flexibility. So I want to increase this number a little bit because right now it's 1. I'm going to set it to, I think 10, something like that. Let's see. So it follows the outline a little bit better versus 1. I think as you can see here. So if I set it to 10, you see it follows a bit more close. You can even set it more high if you want to. Because if you set it to 20. And then the last one is trim. Right now it's set to true, but later on we need to set it to false. So I'm already going to include a Boolean toggle. If I set to false, you see that this is the actual outline of the surface. It always has an overhang. And if you set it to true, it will trim that off. And the last thing I want to show you is the points input, which is also very helpful. If you want to have a bit more control inside the surface, like how it slopes down. And you can do that by inserting some points. So let's do that. Let's put some points. I wouldn't put too much, just like 1 or 2. just so you can control that surface a bit more better. So with a point, these guys set multiple points. And if you insert them here, you see that right now the surface, it tries to follow along those points as well. So you can move these points around and see how they follow, how the surface follows these points. But like I mentioned, like be careful, because the more points you put, the more harder it is to get like a continuous surface shape. The thing is that if we connect all 4 of these polylines, if I do this, for instance, because that's in the end our goal, it doesn't know, or this component doesn't know to which these points belong to which outline. So we can quickly fix that as well. If we use a component called point incurs. So it's this one, point incurs, plural. And these are our points. If I connect all 4 of them, it will basically tell you the relationship if that point is outside, if it's coincident, which means it's on exactly on the curve edge, or it's 2 if it's inside. So I only want to return me the points that are inside. So I'm going to use a larger than component. So I want to check if it's outside. I don't care, because I only want to have the points that are inside my curve. So either coincidence or 2 inside. Best would be 2. So I'm just gonna, filter for 2. So 1. So larger than 1. And then a dispatch component. And the dispatch component goes to our points and a filter list. So now it has filtered out, per curve, which points are inside. It's kind of a crude way, but it works. So right now we have 2 reference points in the first outline. But the good thing is, like, if I move them around, so let's say I move them here, you see that in outline 3 or curve 3, we have just 1 point. Why 1 point? Because this one is not in any outline. But if I move this one here, for instance, you see that it right now belongs to curve 2, curve 1, and curve 0. So this way, it's a dynamic way to kind of, get the points where they are, so you don't have to select them and everything runs automatically. And now you can adjust your, like, the points so they follow the surface. You don't have to worry if you put some more points, you put 1 point here because this one, you want it to be controlled just for the surface. It will automatically recognize that, this point is for this surface. We're just going to focus on the panelization of those roof surfaces. I mean, we could have directly used those 4 surfaces to kind of divide the surfaces and start panelizing them. But I found you have a bit more control if you separate that process. So on the one hand, we have the generation of just the shape of the roof. And on the other hand, we have just the generation of the panel's size and shape. And then we kind of can combine them. We can control both individually a bit more flexibly. Now, this would involve that you'd have to have some other input geometry, which would be 2 surfaces that we're going to draw. And before we do that, the problem is when drawing surfaces on the XY plane, let me show you real quick, is that even though they might seem similar in size and shape, that their U, V, and W parameterization can be different. I'm just, drawing 4 surfaces that I'm just going to transform a little bit different. So these four, they might seem all the same, but actually in reality, they're all different. So I can show you that by, if you select all four of them and you type in the direction command in Rhino, therefore direction, it will display the U, V, and W parameterization. As you can see, all four of them have different orientation. And now you might say, why is that important? Let me show you. So if I select all four and link them into Grasshopper, and let's say we want to divide those surfaces using the divide surface component. And we're just going to divide it some different numbers for the U and V. Like here you see it is that the direction is different. So for this one, the V direction is like in this direction, but in these two, it's this direction. So in this way, they're already different. Let's say if you want to have the same result by defining them. Another way they're different, if I look at the normals, let's say I want to move the points relative to their normals away from the surface. So the points and then the normals like this. You see, in some cases, they were moved downwards. In some cases, they were moved upwards. So in that way, they all differ in a certain way. And that's where this component comes in handy. It's a Python component that I wrote real quick to kind of sort the surface's direction. So if I connect this one in between, you see that right now they have all the same orientation, like exactly how I want it. So let me delete those, clear the values. Let me delete this stuff as well. Let me turn on this component to know where I need to draw those two surfaces on the XY plane. And I'm just going to use the first one, not all four. So we just do it for one and then we can go, because the process is the same for the remaining three. I want to draw a surface that goes from this corner point to here and then the other one covering the other half. So let me go to my top view. So one surface that does like this. And one surface that goes like this. So those are my two surfaces that follow the outline of my roof outline. And let me link them in, just like this. We turn this one off. And then I want to get the surface dimensions, going to my surface tab, analysis and dimensions, just like this. And then if I divide those dimensions by a number, that number will be more or less the unit size of my panels. So just like this. And then I'm going to use the mesh surface component, this one, because using a mesh is a bit more easy than doing this just using surfaces. It's just a quicker way. So you count this guy, V count this guy, just like this. And let me hide my input surfaces so they're not distracting. So this way, with this slider, we can control the size of those panels. So it will try as best as it can to achieve the unit size for this number. And the nice thing is the reason we drew two surfaces, let me show you, is so they would line up exactly where the straight line piece here starts. Right? So if I turn on let me show the wireframe of my surfaces. So exactly in this line, so no matter how I change the dimensions, you will always have a cutoff here. And that's precisely what I want. Let's set it to 1.5. All right. So this would be the panelization of my roof. Really basic. And what we're going to do now is to kind of project this panelization on top of our roof shape. Now there's a couple of ways we can do that. I find the quickest way or the easiest way is to use mesh ray. So that component is under intersect, mathematical, and mesh ray. This one. So it would need a mesh to project it on, and that's going to be our roof. So let me set the wire to hidden because we're going to drag this thing here. I know it asks for a mesh as an input, but it will automatically convert it anyway, so we can just insert it here. Then the points we want to use, those are the corner or the vertices from this mesh. So we need, what do we need to use? If you go to mesh and then deconstruct mesh, just like this, we got all the vertices. But before we do that, I forgot we have two meshes, so we need to join them into one. So if you go to our mesh tab and then here, a mesh join, this will simply just join them into one object. So these are our vertices, which go in here. And then the direction would be the C direction. So we can use a unit vector, the unit C. And this way, they're nicely projected on top of my surface. Let me just turn these guys off. And unfortunately, as you can see, sometimes because it's exactly the edge of our surface, sometimes it misses. It doesn't really hit the surface. Now, a way to remedy that, it's also what I mentioned in the last part, is we can turn the trim boolean. Right now we set it to true, so it will trim off the excess. But right now we need to set this one actually to false. So we have a little bit of overhang, and that also allows us so that all the points are nicely projected on top of that surface. So these are our points that are projected. Now we just need to adjust our original mesh. So we can draw a new mesh using construct mesh. And for the vertices, I'm going to use those new points. And for the faces, we can use the same face list from our original mesh. And that's how we, that's a quick way to just get your, the panelization projected on top of the mesh. The nice thing is if I go to top view, it looks like a square grid. So it's not deformed by the parameterization of the surface. And that's what I was talking about by separating the shapes of the panels and the shape of the roof. So we have, for both, we have a bit more control. And also the nice way is that no matter how I change the size, you always have this nice separation line here. So this is our mesh. Unfortunately, all these panels are double curved, and we don't want that. We want them to be flat panels, so they're ready to be manufactured. And also, we directly can use that rationalization process of flattening those panels to directly get that staggered effect of the roof. So what do we need? We need the corner points. So first we get the boundaries, which are the outlines per face. And the way to get the corner points, you could either use explode curve to get the vertices. The thing is, because it's a closed curve, it's going to repeat the last vertices. Like as you can see here, we have 5 vertices, even though they're quad, so it should be 4. We could remove that item from the list using an extra component, but a quick way to do it is use the discontinuity component. Because the nice thing is that this way we directly get our 4 corner points without having the extra one. Then we're going to get the list item because we're going to create a plane per face. And that plane we're going to use to project all our points on top of, so they all are flat. And that way we're going to create the staggered effect and also make sure that our panels are flat. So this is the item we need to use, and then we need to create a plane. And for that, we also need Z orientation of that plane. I'm going to get that by using the face normals component from our mesh, because these are already in their own branch. So we have to graft the normals. And we're going to construct a plane. Now there's various ways to do that. Right now, we're just going to use the plane normal. This component just requires an origin and the Z-axis, the normal axis. So the origin would be that point that I selected here, basically the first corner point. And the Z-axis would be this one, like the normal of the face. So that's our plane. The only thing is that sometimes they're not aligned properly. So that's the next thing we're going to do. We need to align them correctly. And we're going to do that by getting the other corner points. And I'm going to draw a line from our origin point and the next one. So we get a diagonal line because that's going to be the orientation we're going to use to orientate this guy. So there's a component also under vector plane, and it's called align plane. This one. So this is our plane we want to align, and then the direction, that's that diagonal line that we just drew. And this way, if I turn everything off because it's a bit of a mess, you see right now that per face we have a plane that has the normal of the entire face and is aligned along the diagonal line of that face. Right? And they're all facing the same way. Now, the next thing we want to do is we could already project our points on top of this plane, but we kind of want to rotate the plane a little bit to kind of exaggerate that staggered effect a little bit, let's say. So the way I want to rotate this plane is, again, along this diagonal line. So there's a component under transform and under Euclidean and then rotate 3D. So the geometry we want to rotate is our plane. The angle is a value that I'm going to specify manually. It's in radians, so we need to, I prefer to insert it in degrees. So I'm just gonna, I don't know, minus 30 to 30. And let's set it to 5 degrees. So the center of rotation, that would be again our origin point that we use for our plane. I know it's better to deconstruct that plane. We get the information directly. Let me go to vector, and in the plane there's deconstruct plane. So if I connect it here, I get the individual values. So it's basically deconstruct point, but for a plane. So I have the origin. That's great. You can go directly in here. And then the axis, like this. So now supposedly, yeah, I'm rotating exactly around that diagonal line that I showed here. So that's perfect. So now we have our plane. So the next thing we need to do is to kind of project that like double curved face on top of the plane so we get a straight flat panel. So for that, again, we need to get the points. Let me move this one a little bit down. We get again our corner points. And I'm going to draw a straight line up by using the SDL component, line SDL, which requires a start, a direction, and a length. So my start's going to be all those points, and then direction and length already, you can leave them as default because direction is already set to the positive C direction and length is 1, that's fine. And then we want to look for the intersection event between that plane and those lines. So there's a component under intersect and then mathematical and line plane. So this would be our line, this would be our plane. So we have all our points projected on that plane. So we can use the polyline component, polyline like this, and make sure to set it to closed. So we can use a Boolean for that. These are all our flat roof panels. And to prove you that they're actually flat, we can use a boundary surface component, this component. And here you see it. So now we have our roof nicely done. And that's where this component becomes really nice, because we can exaggerate basically the staggered effect of the roof. And the nice thing is that right now the orientation of the staggering kind of goes from this corner to this corner here. And I'd rather not like that. I'd rather start them here going from there. So we kind of need to rotate them all 180 degrees. Now the cool thing is that the way this definition is set up is that we can actually achieve this by changing the index, like our origin point. So we can insert a slider here from -2 to 2. And make sure you have your wrap set to true. By default, true, so you don't have to worry. And if I, let's say, set it to 1, you see that the direction of the orientation of my staggered panels, they change like this. So in this case, we want to set it to 2. So right now they slope down towards there. Let me increase this value a little bit. Just like this. And the only thing missing is to give these guys a little bit of thickness. So we can just use a extrude component, the regular one, this one, extrude. And direction, we want to go in the C direction. And we need to go negative. So I'm just going to use a negative. And then a value. So just a regular number slider from 0 to, 2, like that. Let's say 0.5. And here we have all our panels. And if you want to get the bottom part as well, we need to move just those flat panels that we created. We just need to move them down with the same amount we specified here. So this one goes in here and one goes in here. So we have the bottom part as well. These are our final results, basically. So I can select all of them, hit insert, or go to solution and bake to get them into Rhino to see how it turns out. You can go to a rendered view, and here you have your staggered facade panels. And all these elements, they're all standardized basically, but standardized in a way that they can be, they're not double curved or anything. They're just straight boxes basically that just are skewered a little bit. They're all easy to manufacture, although they're all different. it already has a bottom, because this one I'm extruding the surface and not the line. So I'm getting on the bottom, I'm already getting the closest thing. If you want that to be separate, wait, let me undo my baking. Instead of extruding the surface, just extrude the polyline. So this way, if I bake these guys, for instance, they're not closed on the bottom. So you can bake separately the bottom parts and the top parts if you want to apply material, something like that. So it's a very quick and basic way to kind of get this panelization on top of double curved surface, but still kind of rationalizing until a certain point all the panels, for already having in the back of your mind, like, hey, how am I going to build this thing? So I hope you enjoyed this exercise. Let me know what you come up with in your project. Hey everyone, congratulations on completing this exercise on the Jinji Lake Pavilion. Today, we explored how to break down a complex roof structure into manageable parametric elements using Rhino and Grasshopper. You learned to work with catenary curves, create continuous outlines, generate precise surfaces, and rationalize panelization. Key skills in computational design. Now, if you found any part of this exercise challenging, now don't worry. In our platform, Think Parametric, we offer courses designed to strengthen your fundamentals in both Rhino and Grasshopper, from complete beginner to advanced levels. Our Grasshopper Fundamentals course and Rhino Fundamentals course are tailored to help you build a solid foundation or refine your skills even further. And there's even more. Besides these two courses, our platform covers a wide range of topics essential for the building industry, including BIM, 3D modeling, graphic design, visualization, and much more. We're here to provide you with the resources and expert guidance you need to excel in today's competitive design environment. Thank you so much for joining me today. Your progress in mastering these techniques is a big step forward in your design journey. For more learning opportunities and support, check out thinkparametric.com. See you there.